Okay, so in this example, we're given the fourth term of a sequence, and that's 125. So write that as a sub 4 equals 125. And also the 10th term of a sequence is 125 over 64. So find the 14th term. So how can we do that? Well, we can use the nth term formula. So 125 equals the first term times the common ratio to the 4 minus 1 power using the nth term formula. And the 10th term would equal the first term times the common ratio to the 10 minus 1 power. So I'm going to change that to a 3 and change that to a 9. And what we could do is take these two and divide them. We're going to divide them in the opposite order. So a sub 10 over a sub 4 is equal to 125 over 64 divided by 125, which is the same thing as multiplying by 1 over 125. So let's do that. So times 1 over 125, which simplifies to 1/64. And then if we use this side of the equation, a sub 10 is a sub 1 times r to the 9th over a sub 1 times r cubed. Alright, and that's going to simplify to r to the 6th. So we know, okay, 1/64 is equal to the common ratio to the 6th power. So then we could take the 6th root of both sides, and the 6th root of 1/64 is 1/2. And you can use a calculator for that, but you should know the algebra to get to this point. Once you know that, you go plug that in to one of the original equations here. Alright, and then I'm going to erase a little bit. Alright, and then plug in what you know, plug in the ratio, the 125 for the fourth term, 3 for n, well 4 for n, 4 minus 1 is 3, and then solve for a sub 1. So we get 125 equals the first term times 1/8, and then multiply both sides by 8, and we get that the first term is equal to 1,000. So now we have our nth term formula, which is 1,000 times 1/2 to the n minus 1 power. So if we wanted to find the 14th term, we can just plug that in right there, and it's going to be 1,000 times 1/2 to the 13th power. And the 14th term comes out to be like around 0.122. Okay, so here's how you find the sum of a finite geometric sequence. You actually can find the sum of an infinite geometric sequence under certain conditions. But the formula is right there. You just have to know how to use it, and you just plug in the first term for a sub 1, the ratio for r, and then n for the number of terms in your finite sequence. If you're interested in where that formula comes from, if you open up the notes that I'm using, you could click on this link and it'll explain where it comes from, but you don't really need to know that at this point, but it's interesting if you want to read that article. For a finite geometric sequence, for infinite geometric sequence, the formula is similar, but it's just a little simpler. And it's actually, if you compare it to the formula for a finite geometric sequence, which I'm writing right now, if you imagine that that n was infinity, and as long as r has an absolute value less than 1, like something like not equal to 1, but less than 1, then this part would just equal 0. So if you think about it, like let's say r was like 1/2. If you just kept raising 1/2 to a higher and higher power, like 1/2 squared is 1/4, 1/2 cubed is 1/8, 1/2 to the 4th is 1/16, that number would get closer and closer to 0, which pretty much just gives us this formula right there. So if an infinite series is said to converge, like get closer to a sum, if the common ratio is in between 1 and -1, and it's said to diverge if it's bigger than 1 or less than -1, meaning it gets farther away from a specific number. So if you did like something where the common ratio doubled, like 1, 2, 4, 8, 16, and you kept adding those numbers, the sum would diverge. You'd get farther and farther away from the previous number. But if you did something like 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, the sum would get closer and closer to 2. All right, and that's what we'll look at in the next video.